Okay. Oh, thank you very much, Larry, for the invitation to come here and for the opportunity to speak. As you already note, this is going to be a talk using slides. In this sense, I may be a little atypical as a mathematician because I always like slides. I have to say I feel a little bit more comfortable using slides, but I'll write something on the blackboard now and then if you're... Okay. So this lecture will also be about the Picard-Fuchs equations, except it will be on the arithmetic side. And let's start with something which is actually a G function. So I'll start with a power series which has integer coefficients. I call the power series F. I call the coefficients G, which is a bit strange, but it's historical development which made me do this. And I forgot to add that the radius of convergence should be positive. And I suppose that it satisfies a linear differential equation, which of course has a certain minimal order. So in that sense, it is a G function, as discussed by Javier in the previous lecture. So we're back on a similar topic. And well, a situation like this, if you try to find power series with integer coefficients satisfy linear differential equations, and you try to do that on a computer, you're going to have a really hard time, actually, because they're actually very rare. And so I like to summarize this by saying that most linear differential equations do not have a solution with power series having integer coefficients. I hope you don't ask me what you mean by most. So, you will see. So that's precisely, it turns out that only the examples that people give, it always turns out, however complicated they're looking, they always turn out to be to come from algebraic geometry in the sense that Javier explained. So it always turns out that, as implied by the Bombieri-Dwork conjecture, which I phrased here in a very simple situation, namely, if you have a situation sketched like that above, then the differential equation involved basically comes from algebraic geometry. So it's a Picard-Fuchs equation, as people would say. Now, Picard-Fuchs equations, as Javier explained, they arise from Gauss-Manin systems, which you have on families of algebraic varieties. And what I like to discuss here is a very simple, concrete construction of a family of varieties associated with Picard-Fuchs equations, which is pretty concrete and also involves some examples that you have seen before. And the second thing that I'd like to discuss in this lecture, and it will be actually the main theme, namely that if you look at these coefficients GK, then very often they turn out to have very interesting arithmetic properties. Most of the examples that people know of differential equations having these integer solution power series solutions, they come from combinatorial sequences. So for example, the GKs, the well-known numbers, for example, binomial coefficients or a priori numbers or a priori-like numbers, such things. And well, these are all things that come from algebraic geometry. And it turns out that people who are, if you look at the online sequence of integer sequences, then you find many examples of them there. And people are very excited to find all sorts of properties and congruence properties. And that's precisely the thing I'm going to be interested in here. Okay, so I will construct a class of Picard-Fuchs equations. And to do that, I'll start with a Laurent polynomial in, well, n variables. And this has a Newton polytope. So if you look at the support, that means the exponent vectors which occur in this Laurent polynomial, you put them in the plane or the space. These are integer points. And you look at the convex hull of them. That's the Newton polytope. And the assumption will be that this Newton polytope has a unique interior point. I'll give a few examples. Here you find them. And now I use this opportunity to use the blackboard. So for example, take the first one. Well, the support of this, so let me draw a plane here. Here's some lattice points. And the support of this polynomial is, of course, this thing that corresponds to the x, this point which corresponds to the y, and this which corresponds to the 1 over xy. And the convex hull is basically this triangle. And if you look at the interior of this triangle, you see that the only lattice point in there is the origin. So this satisfies this thing. Here's another example that you can work out for yourself, which is maybe more interesting. And well, you have to do the multiplication yourself. I draw the picture. So here you see the x, you see the y, the 1 over x, the 1 over y, and then of course there should be x times y, and there's a 1 over xy as well because of the last factor. And then this will be the Newton polytope, and of course again in the interior the origin is the only point with integer coordinates. So there are many examples you can, despite this condition, we can, well, sky is the limit in that sense. I also put down an n variable example to make it interesting. And of course, this n variable example is, I call it the diagonal case. And of course, the Newton polytope is a generalized octahedron. Yeah, so then that also has the origin as a unique lattice point in its interior. And now we're going to be interested in the family of algebraic varieties given by this equation, where t is the parameter. That's a one-dimensional family and a very simple type. And what I'd like to do now is to determine a period that corresponds to this particular family of varieties. And in order to do that, I will construct a so-called constant term sequence, which consists of taking this Laurent polynomial, taking a kth power, and then taking the constant coefficient of that. And so you get a sequence of numbers, gk. People usually call this constant term sequences, and they're very often studied in, well, by people who are interested in combinatorics and similar phenomena. And so all these gk's are then my formula for constant term is CST, as you already can guess, and then that's what I use for constant term. So this ft is then the generating function of this constant term sequence, be compatible with my notation. You see big F on almost every slide. So. Okay, and then if you sum this constant terms, you get, of course, the constant term of the sum, which is also a bit of a misnomer, as you can see, because you have well, you can argue about whether this is mathematically correct or not, but I like to say it this way. And now my statement is that this constant term of that sequence there is equal to this repeated integral of that same series, which you find there. And well, if I carry out the, sorry, I can give you the slide if you want to. Okay, sorry. Yes. Am I looking at, sorry, what? Yes. Yes. That's going to be the next one. That's going to be the next one, yes. But it's this one. Okay. And well, I guess I don't have to say that taking constant term of a Laurent polynomial is the same as integrating over a circle of radius 1 with these types of differential form. So I'm assuming that you know this. I had prepared to explain it, but it's not sure if it's necessary. So what you see here is basically something that looks like a period. And actually, it's it's slightly different from period because the integration takes place on the points which you have to choose t small enough in order to make that converge. And so basically, the integration takes place over the complement of the variety. So we're in the ambient space, but it's a nice rational differential. And then you can turn it into a integration over the variety itself by taking certain Poincare residues, but I'm not going to do that. So I like this better. This has my preference. But now at least you see that you can consider this as a period of the de Rham cohomology, well, actually of the complement of this, and you can relate it to the de Rham cohomology of the variety itself. So let me give you some examples of these periods. So if you take that polynomial, which is a product of two things, take the constant terms of the powers, you get the squares of the binomial coefficients. And I think this has occurred several times in, well, I noticed Duco's lecture last week. He talked extensively about this, this particular example with the squares of the binomial coefficients. Duco used another G, but you can use this one as well. Here's another one. It's the polynomials you see over there. And if you there take the constant term sequence, you get the sum of the cubes of the binomial coefficients. Eighth binomial coefficient, and those are called the Fresnel numbers. That's probably a historical name, so it must be someone from the 19th century. And here's another one. So after the a priori numbers were introduced by a priori, people started working on it and discovered all sorts of arithmetic properties. And one of them was, for example, that this is a constant term sequence of that polynomial G that you find over there, so, which is not trivial. Yes, yes, yes. So we'll not forget that. So, and so checking that this has a unique, the origin as a unique interior point is already a little bit of work, but proving this as well. Here's another example which I like very much. It's an n variable example. And it's just, you just take the sum of the variables and you multiply it with something which involves the sum of the inverses of the variables. And if you look very carefully, this also has only the origin as the interior point of the Newton polytope. And these, in the case NS4, this is called the Huylek-Verel family. I'll just call all of them for all possible numbers of variables. I will refer to Huylek-Verel. It will probably occur 1 or 2 times more during this lecture, depending on what we're going to do. And well, if you have such a situation, you have this generating function, which is clearly, which I hope I convince you of now, a period, then you can show that this satisfies a linear differential equations with coefficients in polynomials with integer coefficients. The reason why this is possible is, well, for this we need an explanation on the finiteness of the dimension of the relative de Rham cohomology, which I'm not going to do here, but this is a very nice fact to state and to use. Okay. Now we come to the first arithmetic statement concerning these coefficients of Picard-Fuchs equation, and it's something that people call Lucas congruences. So if you look at the construction I've just made with this Laurent polynomial, with this unique interior point, which is the origin, do this construction and take a look at the constant term sequence, then these constant terms of GKs, they satisfy a congruence relation, which is known as the Lucas congruence. And what is it? Well, it turns out that if you take a particular coefficient, GK, and you write the K in base P, where P is any prime that you can think of, actually. So that means K is equal to this combination of powers of P, where the coefficients Ki are between 0 and p, that's the base p expansion, then it turns out that in order to get g of k, all you have to do is determine the g's with arguments which are between 0 and p and multiply them. For computational people, this is great because it means that these GKs can sometimes be very complicated numbers, and but you can compute a modulo p quite easily by using this speed up by just multiplying the g's at the digits, basically. So for computational purposes, this is very nice. I say here it's a theorem of Samol and van Straten. Well, congruences of this type are very familiar. There are many sequences which satisfy this, and this was noticed very much before 2008 also by other people. However, the statement of this theorem which you have here, the earliest proof, complete proof I could find was in a paper by Samol and van Straten. I know there's some people here who know more about these Lucas congruences. So if you have a reference for a proof that goes before this, I would really like to know so I can change the it. Yeah. This is in the context of the construction that I just did, and the unique interior point being the origin is essential there. If you have more interior points, then this doesn't hold. You have to do. You can state something like it, but you have to do a matrix version of this, which I'm not going to do here. I'll just keep it like this. Okay, this is my favorite baby example. It's a sequence which consists of powers of 2. So that also satisfies the Lucas congruences. So if I take 2 to the k, and I write this k in base p like that, and it turns out if you look at it modulo p, then the powers of p in this exponent will disappear for the very simple reason that 2 to the p is 2, 2 to the p squared is 2, 2 to the p cubed is 2, etc. So it's elementary Fermat's little theorem. So you get in the exponent, you simply get the sum, which of course becomes this product. And there you find the Lucas congruences for this sequence of numbers. Of course, it's a very trivial example, but it's also the reason that I find all the more miraculous that in these more general cases, there are similar congruences that seem to hold. So there's a kind of analogy that persists in this sense for particular Picard-Fuchs equations. So what I like to do now, I like to give 1 or 2 proofs, and for that I need a reformulation of the Lucas congruences. So what I do is show you a lemma which replaces the Lucas congruence by something something more functional. So if this f is still the generating function of these coefficients, then I look at the truncated polynomial. So you have the power series, it's called big F, it's a generating function for the GKs. I truncate it at p. So all the terms of order less than p are involved. That's called fp of t. And people who have been at Duco's lecture last week, he also introduced an HP, which was also a truncated polynomial. So this is also a bit of the direction in which this goes. Anyway, if you weren't there, doesn't matter. It's just a truncated F. And then the statement is that Lucas congruences are equivalent to the equality of those 2 sides modulo p. So ft is basically the truncated polynomial times f, where t is replaced by the p power of t. It's a functional relation. And this is what people call a Frobenius factorization, because t to the p is the Frobenius lift of Frobenius of t under the p Frobenius. And so it's kind of factorization. And actually, this is let's say, a baby version of a Frobenius structure. So the Frobenius structures were a subject of several of the lectures last week. And there you have Frobenius structures basically give you a relation between the solutions of a Picard-Fuchs equations and the solution of Picard-Fuchs equations where you have replaced t by t to the p. And they are related, it turns out. And here you see a baby version of that, namely this multiplication property of this f. So it's the very first statement. And of course, if you write down the Frobenius structure in general, you also get the other solutions there, but here you don't see it for the moment. We have left them aside and considered everything mod p, which gives you this simple thing. Okay, let me show you why this is equivalent. My statement is that the Lucas congruences are equivalent to ft being a product of these truncated fp's evaluated at t to the p squared, etc. And well, I guess if you, a moment's thought, so to speak, will show you why this is true. Because if you want to determine the coefficient, case coefficient of ft, that gives you, of course, the gk. And if you want to do it on that side, well, you have to pick a coefficient from each of those factors. And in order to, because of the structure of this base p expansion, you have to take the k0th coefficient of fp, the k1st coefficient of ftp to the p, etc. And so these factors on the right, they give you the digits, so to speak, and that gives you the product structure. And of course, if you rewrite this, well, you notice that this after fpt, then basically you get the whole thing repeated with, except that you replace t by t to the p. So therefore, after fpt, you get ft to the p all over again. So, and this is the Frobenius factorization that we wanted to have. Hope that I'm here so far. And I'll show you an example. So I'm going to do my baby example again, so the powers of 2. And of course, the generating function is this geometric series. It's a geometric series of that rational function. And I'm going to rewrite this rational function in a more complicated way, except it's also a very useful way, although even though it's complicated. Namely, I'll replace the denominator by this, and I compensate with this numerator. And now the thing is, I would like to consider this mod p. And if you consider it mod p, this 2 to the p becomes 2 again. And the numerator stays the same. And what you find now is that here you have your ft. This is the truncated ft. And here is the denominator of ft to the p. And there you find your identity. And the nice thing is that also, this also goes through for all these constant term sequences in our situation. Okay, now I'd like to, I'm not going to say clobber you with a proof, but I'm going to give a proof for these Lucas congruences. And the reason I like to give it is that despite that looks quite deep, it's essentially, it's very elementary. So it's a one-page proof actually. So I'd like to, I think it's such a nice proof that I'd like to show it here. And well, actually it's going to take 2 slides, but I hope you forgive. So, but I need some reminders first. The first reminder is that, well, we saw this already. Ft is the generating function of the constant terms, is the constant term of the power series, and we can basically consider it as the constant term of this rational function with some abuse of interpretation and notation. Yeah. Okay, that's the first remark. The second remark is the Cartier operator. So the Cartier operator, you can let it act on rational functions or power series if you like, but let's do it for rational functions. The Cartier operator of a rational function consists simply of this average of all values of the rational functions in the p-th roots of these x of x. Perhaps I should, I forgot to say something. I lost my chalk. by the way, I forgot to tell you, but I suppose you guessed it. Whenever I write boldface x, I mean all coordinates x1 up to xn. And whenever I write boldface x to the power boldface k, it simply means this product. Yeah? So that's the notation that I use here. And so basically, you take the average over all values of r at the pth powers of x, so the many pth powers actually, and you sum it again, you get another rational function, which looks in general much more complicated than the thing you started with. But let's keep that in mind for a moment. Sorry. P is not boldface, no. But then you raise the whole thing, the whole monomial to the power p, yes. Okay. And furthermore, if you take a Laurent polynomial like this, then the effect of the Cartier operator is that this Cartier operator seeks out the monomials which are raised to some pth power, and it divides the exponent by p, and that's the only thing. And all the other ones are discarded. And the effect of it is then that you get this new Laurent polynomial. So these are the things I'm going to use, and I'm going to use one further thing, namely, that if you take the Cartier operator of a rational function of x to the p times subrational function, well, the nice thing is that if you look at the definition, then and stare at it a few minutes, you can see that you can simply take this out. And so it follows from the formula of here. You can take out this x to the p, take it out, and get s of x in front of the Cartier operator applied to t. So these are this is the Cartier operator, and that's basically all you have to know about the Cartier operator. So now we get to the proof of the Lucas congruences, and I'll do that again step by step. What I'm going to do, and it has some similarities with the sequence of powers of 2 that you just saw. So it's reminiscent. What I'm going to do is compute the Cartier operator, Cartier image of that rational function. And of course, it's a rational function again, but quite complicated. However, my claim is that if you look at it modulo p, you again get a very simple rational function, it turns out. And to see that, you can do it step by step. Namely, you rewrite this 1 over 1 minus tg in a more complicated form, as we did before, but it's a very useful form. So you have that thing with a strange numerator again, and this pth power in the denominator. Now I like to look at it modulo p. And if you look at it modulo p, there's a gx to the p over there, and you can take the p inside the parentheses. So I hope you can see what happened, because there's only one place where it's different. So we drew in the exponent p, which was on top of the Laurent polynomial, and you can draw it inside, and you get the x to the p, which is an effect of looking at things modulo p via a little theorem of Fermat. Now we have a Cartier operator, and now we have a function of x to the p. We can take it out. So let's take it out. And then what we left is that the Cartier operator should now act on this numerator, divided by that the 1 over t to the p times g. Okay, now we're going to apply this Cartier operator term-wise to these powers of g. So let me take this example once again. So if I take for example, with this g that we have here, we take the kth power of that. Well, the Newton polytope of this, I can slightly change this drawing by saying, well, this is the point k comma 0, and this is 0 comma k, and this is k minus k. So if you take any term that you see on this numerator there, for example, the kth power, apply Cp. Well, like I told you, Cp seeks out the pth powers of monomials. And so we have inside, remember, k is less than or equal to p minus 1. So what are the vectors which are divisible by p inside this triangle? Well, it can only be the origin. And for any power going up to p minus 1, as soon as k becomes p, then of course you get p powers there. But we stop at that moment because that's how this truncated sum is made. So the only point whose coordinates are divisible by p is the origin. So this Cartier operator, when acting on d to the k, it only selects the origin and it reproduces the origin. So that's what you're left with, and what you get is this summation. And now you see the truncated generated series over there, this thing that we called Fp of t. You have it, and okay, we're almost there. Turns out that the Cartier image of that rational function is this rational function, which is also quite simple when considered mod p. And what we're now going to do is these are still rational functions. We're now going to take the constant term on both sides. Well, the thing is that taking a constant term commutes with the Cartier operator, which you can see trivially, and therefore the constant term of that will reproduce precisely this ft. Well, this one we have already seen, it's over there. And if you take the constant term of this, you also get the f, except that t has been replaced at t to the p, so you get this. And this was our version of the Lucas congruences that you see over there. So this is basically the proof. Okay. I don't know if there are questions. So. Yes, that's because of that argument that you see over there. Absolutely, yeah. So, and of course, if you have, for example, two points in the origin, then you have basically you can reproduce two sequences, one corresponding to one point and the other corresponding to the other point. It gives you two sequences, and then you can, with the same argument, you can produce a matrix version of these Lucas congruences. But usually people find them less interesting than these single ones, so I like to stick there. Okay. I noticed that Don Zaguet is not here this week. I hope he has been here last week. Also not. Okay. So now I'm referring to Don Zaguet's lecture. Yeah, okay, well, that's really too bad. Okay, well, maybe I could say at least an epsilon of what you wanted to say. So the second part is going to be about the relation of some Picard-Fuchs equations with modular forms. So I'm not sure what pre-knowledge I can expect of modular forms. I'll just pretend that you know something about them. I hope all goes well. So anyway, so modular forms are complex functions on the upper half plane that are invariant under a certain discrete subgroup of SL2R. I call that group gamma, and I suppose that it's finite co-volume. So if you take the quotient of the upper half plane with respect to group, you get something with finite hyperbolic volume. And then there are functions that are invariant with respect to these transformations, and we call them modular functions. Now, it turns out that the modular functions form a field, and for some gammas, or for many gammas actually, this field can be generated by one modular function. In that case, we call that generator a Hout model in proper English. So this is usually called the Hout model. So it's a generator of the function field of the corresponding modular curve. And then if you have a modular form, modular form is also an analytic function. It's analytic on the upper half plane, which satisfies certain transformation properties with respect to that same group, except that you get some factors in front. And these are modular forms. Now, suppose you have a modular form of weight k. That refers to the, should I, I'm not sure if I read. Okay, yeah. Yeah, that's a definite possibility, yeah. Sorry? No, there's a, well, I actually in the things to read for this lecture, I suggested an article by Don, so there you can read it. Even a particular section, yes, yeah. Sorry? 1, 2, 3. Yes, so that would be another example. Okay. I think so. We're safe. Yes, okay, we're good. Okay, so we have a modular form, and now you can. So this modular form, usually the variable is tau. Tau is the coordinate of the complex upper half plane. That's usual with modular forms. But you can also rewrite it as a function of t, this half model. But you can do it locally because t cannot always be inverted. So you do it locally, and you get some function that we call f. F again. And it turns out that Don wanted to show that f satisfies a linear differential equation t with polynomial coefficients t, which is actually it's not so very difficult to show. You just have to think of it. That's basically the idea. And this was also known to 19th century mathematicians like Felix Klein and others, but then forgotten for some time. And I think Don revived it in many of his lectures, and so it's. So what I like to do now is reverse this procedure of going from modular functions to modular forms. I would like to start with the differential equation and then recover the modular form and the modular function. So I start with a differential equation, and yeah, I tried my best to make this as brief as possible. It looks like very much, but it's not really. Actually, you can also forget it afterwards. Namely, look at the differential equation of order n, and theta is something that I think Duca also used, the theta. Theta is basically the operator t d dt, which is much more convenient if you work in the setting of these differential equations where you pay specific attention to the origin. Yeah? So the LIs here are polynomials. I take them to be integer coefficients. You can make it more general, but I'm not doing that. And the assumption is that the leading polynomial is 1 if you put in t as 0. The other ones are all divisible by t. So if you put in t as 0, they become 0. So, and there's a name for this. It's a mum-type differential operator. Mum being maximal unipotent monodromy at the origin. But you need not concern about that. I don't want to tell you a lie, so we're going to start with this, and then you can forget about what it means. So we consider a Picard-Fuchs equation of mum type, and you can forget what mum means. And what we do now is that if you have a mum type differential equation, there's a unique holomorphic solution at the origin. So let's call it F. And it's unique once you fix the starting term, which is taken to be 1. And there's a second unique solution of the form f times log t plus gt, where gt is a power series, and which we can normalize so that it starts with 0, with the constant term 0. Let me give an example. This is the running example throughout these 2 weeks, I think. It's this, but written slightly differently. I renormalized the t. But anyway, the solution, the holomorphic solution that I mentioned here is this one with the squares of the central binomial coefficients. Very well known, the Legendre function. And this is a twist of the so-called Legendre equation, which has been displayed several times. But maybe the GT hasn't been displayed so often. This is the GT. And well, of course you recognize this, but this looks more complicated. And the point also is that these coefficients are not integer anymore. You have a big supply of denominators, and certainly these coefficients certainly do not become integers. But it's nevertheless a solution. Now what we're going to do, we're going to recover the modular form and the modular function which underlies this, this whole thing. So we define the so-called canonical coordinate. You take that very thing g from the second solution, divide by f, take the exponential, and multiply by t. This is known as the exponential of the Schwarz map if you work with second-order differential equations. So it's called the canonical coordinate. If you ask me what is the coordinate of, well, I don't, of some family of curves, but never mind that, we call it the canonical coordinate. And now it turns out, of course, this qt is again a power series expansion because g starts with the constant 0, so it's you can exponentiate that power series, producing another power series, and the coefficients are, of course, they're rational. And so that's a trivial remark. The second remark is less trivial. It turns out that despite the fact that this g has lots of denominators in its coefficients, it turns out that this strange combination has integer coefficients, which is very weird, very surprising. And this happens also very often with these mum-type differential operators. A very strange phenomenon. And now you can if you start with Picard-Fuchs equations, this is a very regular phenomenon. Yes, I cannot specify immediately what I cannot formulate any conjectures or theorems about this, but this is what happens in my experience all the time, almost. It's not sporadic. And it's not. If you work within the Picard-Fuchs equations, this is a very regular phenomenon. And so I hope now you take the inverse power series, is called the mirror map. I don't know, that's a name that's familiar before. And it turns out that in our example, we get that this inverse of that canonical coordinate. You can produce a formula for that, which you see over there, this infinite product. For the running, in our running example, yes, the running example is the Legendre example still. Yes, sorry about that. So we get this t, and it turns out that if you substitute this power series, which starts with a q, in our f, which has these squares of the monomial coefficients, you get another power series, and it turns out to be a very elegant looking, it's a square of two theta functions. It's a square of a theta function. So basically it's q to the power, and then you take all sums of squares of integers, and that's, I think it's an amazing identity. And it was well known to Felix Klein in a time when people were working very much with hypergeometric series and the connections with modular forms. So for example, this is a well-known product expansion for a modular function known as Klein's lambda invariant. So here. So this t is also a well-known classical function, and this relation is also a well-known classical identity. But nevertheless, I still find it miraculous that it works. Okay, so this is an example of a connection between modular forms and modular functions with f, which satisfies the second-order differential equation. Now, I forgot what the next slide was. Ah, here. Yeah. Yes, it's all related to families of elliptic curves, actually. So basically, this f with the central binomial coefficient, this Legendre example, is of course given by a family of the periods of a family of the Legendre family, And Legendre family, well, it has the period lattice of these elliptic functions are closed. Well, they're parameterized by a tau. And this is the tau that you see of why you don't see it, because Q is e to the 2 pi I tau, or pi I tau. And this is more or less the relation. So the point is that if you take monodromy, then this lattice undergoes a change, which means the tau undergoes a change, and this will give you the modular group. And this modular group will be the monodromy group of that Legendre differential equation. I think that's the, yes. That's right. And so it's a weight 1 form, and I think these coordinates, they have weight 2. These are Weierstrass, and they have these squares, so I guess it's weight 2 then what you get. But they're probably quite related to that. You can actually, so there, if you use elliptic curves, there are lots of ways in which, for example, such a modular form would arise at some value of a coordinate on the Legendre curve at a torsion point. Okay. So this is what Don, this is the theme of Don's lecture and also of this lecture. It turns out that if you carry out this procedure that I just sketched by taking this quotient and this exponential construct in the mirror map, turns out if you start with the second or third order differential equation, that in many cases you will get just modular forms and functions, surprisingly. If you take a fourth order differential equation, then this construction will not give you modular forms and functions in general, and it's still a mystery as to what you're getting at that point. So, but let me stick to NS2 and 3. So I said in many cases, you do get a mirror map then in order 2 and 3, and so you get a t, which turns out to be a modular function, and okay, now I'm going to commit a small sin, namely I'm going to introduce a context-dependent notation, namely anytime I write t of, so I started out with t of q. And I said, well, q can be the exponential of the tau. And I don't want to write t of e to this exponential all the time. So whenever I write t of tau, I mean this thing with the exponential. I hope you forgive me that. It hasn't bothered me very much when I wrote, and I hope it doesn't bother you either. So, so and furthermore, you have this relation between the modular form and this f of t, which was the relation which I just sketched in the Legendre example. And then it turns out that this, if you substitute this t into this f, you get a modular form of weight 1 or 2, depending on the order of the differential equation that you started with. That's what you usually get. Now, this is rather vague, I have to say. So what I'll do is I'll give you an explicit example. Very explicit. So it's a third order differential equation that you see here. It is certainly of Mum type, because if the leading coefficient, if you take t is 0 there, you get 1. And the other terms, if you substitute t is 0, you get 0. So it has a required type. Now, if you do this mirror map construction, it will turn out that the t has this nice infinite product. It doesn't always happen that you get infinite products, but I've taken examples that do, so put them here. And it's, well, this is a Hout model for just modular group, if it means anything to you. It's gamma 06 extended with the standard involution on it, the Atkin-Lehner involution. And the z, which you get, can also be written as an infinite product, and so you get this. So you get some very funny-looking, interesting examples. And I forgot to say that if you take the holomorphic solution of the differential equation, you get a generating function of the a priori numbers that correspond to Z03. And this is then the modular background that Don wanted to explain. Okay, so. Okay, now I'd like to discuss a theorem, a recent theorem. Sorry? Hang on, sorry, going up again. So if I, yeah? Yes, you get a solution corresponding having this G, right? Yeah, yeah, yes. And so this, so where is the G? You mean here? Yes. So basically, the quotient of these first two solutions involving the log divided by the holomorphic one is your tau. That's essentially, and that follows from the construction. If you go from modular forms to differential equations, that you can recognize that. If you look at in Don's notes, then you see it. So. And you have further ones, and these correspond to the powers of tau. So that explains if you take the Galois group of these higher order differential equations arising from modular forms, you basically get powers of SL2. Symmetric powers. Yeah. Yes. I wouldn't know offhand, but I know many people in many papers have given such lists, and I think one recommendation I can give, for example, is to look at the modular form database, LMFDB, I think it's called. There you can, well, basically, if you look up modular forms, for example, they always mention if there's an A dot product factorization. And so I would have to dig to find such examples. Usually they occur when the modular group has small index in SL2Z, for example. If it becomes bigger, then things become more complicated. So, but yeah, I guess it is possible to compile lists from the existing literature, but I haven't really looked for it explicitly. Okay, well, the last thing I wanted to do is, well, it's not the last thing I wanted to do, but the last thing of the lecture is that show you this theorem, because this is these are Lucas congruences which arise in a different way, and which also has this modular connection. So I'm going to state a theorem, which was put on the archive this year even. And you start with a modular group, which is gamma 0 n, with extended by Atkin-Lehner involutions, whatever that means. You can forget about that. And then suppose that there's a Haupt model, and this Haupt model is, again, a Q series expansion, which starts with Q and then higher powers. And, well, this Haupt model has zeros and poles. You can see the 0 there, that's Q is 0, that's a 0, but the pole is at some other point. And this at some point tau 0. And this tau 0, I put these brackets because it's basically, yeah, the function is invariant under a group, so it's an orbit of this, of tau 0 under the group. Therefore you find these square brackets. And then let Z tau be a weight 2 modular form. And the condition is that it can have zeros at many points, whatever you like, but our condition is that you assume that this Z tau has a unique 0 at precisely that pole of the Haupt model. The order should be less than or equal to 1. Modular forms can also have fractional orders if it's in elliptic points. So now you're going to construct a power series with coefficients gk, which is rather familiar, I think, still. And if in this power series you construct these coefficients such that if you plug in the Haupt model, you get this modular form. So basically, it's the construction of the f out of the given modular form and function, called the gk's. And then the statement is that these gk's satisfy the Lucas congruences for all primes. And the fun thing is that there are many cases where people have no idea about these GKs. So some cases they're explicit, like in the previous example, you saw that these were the a priori numbers. That's also an example of this. And in other cases, these GKs, well, if you have some groups gamma with a large index, with a large co-volume, then there are simply no explicit expressions for them. But nevertheless, people have studied examples of this and wrote down these coefficients and thought, hey, they seem to satisfy Lucas congruences. Why is this the case? And so there's a question you might ask. And this is a theorem which provides the answer, namely that in such cases, these GKs satisfy the Lucas congruences. And in this case, this satisfies a third-order differential equation corresponding to the weight 2 form that we have here. Yeah, so these numbers come from different worlds. I think Hecke operators act on the coefficients of modular forms. Well, these are in a way coefficients of modular form, but I think it's a good, yeah, so you also have to deal with this if you apply Hecke operators. And this is something I've been wondering about, so I think it's a question to think about. Yeah. Okay. So what I'll do is I'll give you a proof, if you're still with me, and because it's also very simple again, and then we're almost done. So the proof of this theorem is that you construct a modular form invariant on the same group that we just had, and of weight 2 times p minus 1, y you see in a moment, such that if you consider the Q expansion mod p, you get 1. They exist, such modular forms. I'll show you in a moment. But suppose we have that. Now the thing is that if you have such a modular form and you divide by this z tau to the p plus 1, then the weight of E is 2 times p minus 1. The weight of the denominator is also 2 times p minus 1. Therefore, you get a modular function. It's okay, it's good. And it has a unique pole because z has a unique pole. And this pole has order less than p minus 1 because the z is raised to the power p minus 1. And so if you have a modular form, a modular function with a pole at this tau 0 of a certain order, and the generating coordinate t also has a unique pole at the same point, it means that this quotient must be a polynomial in the Hout model. And good. And now we're going to consider this mod p. So we take this quotient that we start with. We're interested in ft divided by this because you want it to become, because that's the congruence for the Lucas congruence condition. This quotient should become the truncated polynomial, the truncated fp. And we're going to go in that direction. So this should become a polynomial, which is the truncation of ft. So, but let's start. Modulo p, this is equal to this because of Fermat's little theorem. If you do mod p. If you now substitute t, this Hout model, you get this modular form here, to power p minus 1. If you replace this 1 by the modular form e, you get this modular function, which we have just claimed that it should be a polynomial of degree less than or equal to p minus 1. So it becomes this at modular p. Now if you look to the left and the right, and you want to know what the coefficients of this at are, well, the coefficients can simply be read off from the first few coefficients of f, because this one is going to contribute only from the point t to the p onward. Therefore, you can conclude that this AT should be equal to the FP, right? Okay, sorry. And now we're done, because now we have FPT here, and that's precisely the condition for the Lucas congruences. Okay, how to construct this E? Well, there's a slide, but let me give a hint. In modular form theory, you have something called the Eisenstein series. The Eisenstein series of weight, and this has weight W. Eisenstein weight W. And the point is now that if W, oh, sorry, maybe I should write it like this. If you take W to be equal to prime minus 1, these are Bernoulli numbers. So dW is the Wth Bernoulli number. And the denominators of the Bernoulli numbers are very well described. And in the case when the index is p minus 1, it turns out that this is 0 mod p. So they have a modular form with non-zero coefficients, but if you look at the modular p, you get 1. So this is a property of the Eisenstein series. The series that I just described, this E, is simply a combination of Eisenstein series. So that's how you construct it. Okay, so yeah. No, I wasn't going to show them. So I have 1 page. Okay, so this theory which you just saw, well, so the conjectures that I mentioned were the conjectures by Sean Cooper about these Lucas congruence for the coefficients. So in the case where there are no expressions known, so you have no good starting point to prove this congruence, but via this way you can do it. There's one weight 1 analog that I'd like to show you, and here's a sample application. If you take that modular function over there and this modular form of weight 1, and then you define this series F in the same way as before, you construct this coefficient GK, such that this holds, so the Z is equal to F of T tau. Then these coefficient GK satisfy Lucas congruences for all primes 2 or 23, or the ones for which this Legendre symbol is equal to 1. Yeah. It follows from the construction of that strange modular form E. Sometimes it works, sometimes it doesn't work. And these are the cases where it works. Can it be corrected? Corrected in the sense of, but how? I'm not sure if I understand you. So. Yeah. Oh, I see. Well, yeah. A polynomial raised to a negative power is, well, I can do it, but it's not a polynomial anymore. So. But anyway, I don't want to do it. Maybe later. So you convince me. So this is the theorem, and the surprising thing is that if you look at the other primes, namely the primes for which this Legendre symbol is equal to -1, there these congruences do not seem to hold, strangely enough. So it suggests in a way that these GKs cannot come from the construction that I gave with these Laurent polynomials. So it cannot be a constant term sequence, it seems. I'm not sure. But I was very surprised that the validity of these Lucas congruences depends on the residue class modulo P modulo 23. Okay, so this was my last slide. Thank you very much.